And we'll go on now to our next talk. This is going to be presented to us by Teun Bousema. Teun holds a dual appointment at the Radboud University Medical Center in Nijmegen, as well as with the London School of Hygiene and Tropical Medicine. He'll speak to us today about some of the challenges we face when looking to assess TBVs in the field. Thank you.
Good morning, and I would like to thank MPI for giving me the opportunity to talk. My name is Teun. It's very difficult to pronounce, but my parents call me Teun Bousema. And I will talk about transmission-blocking vaccines and about the evaluation. And as we've heard before, transmission-blocking vaccines aim to have a clinical benefit by reducing malaria transmission, and this is a delayed effect in humans. So in the end, what we hope that a transmission-blocking vaccine will achieve is a reduced incidence of infections. And for some reason, perhaps for good reasons, as soon as we start talking about transmission-blocking vaccines, you see complicated faces. This is going to be difficult to get registered. It's going to be very difficult to evaluate. And I'm not such a pessimist. I don't think there's any reason for panic. Perhaps that is because I'm not going to talk about phase 3 clinical trials today, which will probably have a cluster randomized design. They are large, expensive, but they're feasible. And I'm not going to talk about them because there's one paper that came out this year by Lucy Tusting in Advances in Parasitology that nicely summarizes all the different readouts for reductions in transmission intensity. And there's also a manuscript being prepared by an MPI technical consulting group. Instead, I'm going to talk about phase 1, phase 2 clinical trials. And I believe that's where we should realize there's a real strength of transmission-blocking vaccines, and we have actually very good assays to help us, provided we have a clear surrogate endpoint for efficacy that we can agree on, that is on the pathway of transmission, plausibly associated with clinical benefit, and one may argue that once we agree on that, there may even be a reason to have accelerated approval based on this surrogate endpoint. So what is the problem? This should be... so how do we measure vaccine efficacy? I will talk you through feeding assays, because I'm not sure if everybody in the audience knows about this. The strength of transmission-blocking vaccines, the ones that are now in development, is that they all work through antibodies. Cellular immunity doesn't appear to play a major role, so antibody responses and antibody titers are highly predictive of efficacy. We also have some functional readouts, and those are feeding assays. And here you see a photographic illustration of feeding assays that can use cultured gametocytes or naturally acquired gametocytes that are offered to mosquitoes in a membrane feeding system. These mosquitoes are allowed to take a blood meal, and after 7 days commonly dissect these mosquitoes and determine whether you have a reduction in the proportion of mosquitoes that have oocyst developmental stages. So this is the way we can evaluate transmission-blocking vaccines. So what is the problem? It's a biological system, and it's poorly standardized, as many biological systems. And the problem is also that until not too long ago, it was considered quite an awkward methodology performed by awkward researchers who discuss among themselves whether it's useful to have smelly socks on top of feeders to increase your feeding rate. Well, try to standardize that. Perhaps more complicated or more relevant than these smelly socks are that groups use different mosquito species, different strains. There was no consensus on the outcome measure. Should it be oocyst density? Should it be oocyst prevalence? And also, there's no apparent consensus on the different feeding assays and where do they play a role in taking transmission-blocking vaccines further. I say apparent because I think actually among researchers who are doing these kinds of assays, we know pretty well what the strengths and weaknesses of these assays are and where they complement each other. So my talk, now first, sorry, I clearly prepared this presentation early morning, thanks to the jet lag. I think we always think this is a weak position, but it's good to compare our functional assays with other assays, like the growth inhibition assay, that is used to prioritize and also evaluate blood stage vaccines. That assay is on the pathway of disease, reducing growth inhibition of invasion, clearly has a role in preventing disease or severe disease. And it's used in many labs, many more labs that have feeding facilities. There's also large inter-lab variability. There are some strain-dependent results, and actually the relation to clinical immunity is not all that obvious. So we like to think as membrane feeding assays something special, something weak, but I think actually we may not be in a very bad position. So my talk will be about the accuracy. Do we measure what we want to measure? Can we measure it sensitively? And also about the precision. Can we obtain the same estimates of mosquito infection rates? And can we upscale our feeding assays so we actually have precise point estimates to really get a more precise outcome measure for our transmission blocking vaccine evaluation? So what do we want to measure? So this is a graphic of parasite development in the mosquito. We have on the left, as soon as the mosquito takes up gametocytes, these gametocytes activate to form gametes that fuse, form a zygote, an ookinete that penetrates the mosquito midgut wall to form oocysts. And these oocysts are very few in numbers. That's actually where the parasite is at its smallest in terms of population size, but they enlarge over time, and at a certain point they burst and release hundreds, thousands of sporozoites, and some of these sporozoites will find their way to the mosquito salivary glands. The latter is what we want to measure. If a mosquito has sporozoites in the salivary gland, it's infective, and a transmission blocking vaccine wants to prevent that. There is, however, a problem with measuring that, because you will have a health hazard. If you have a lab and you wait for sporozoites to develop, and you do that in the field, it means you have infective mosquitoes, infective surviving mosquitoes, because survival is also a problem. The survivorship of mosquitoes after feeding will really be an issue if you wait too long. And if you have to wait 12, 14 days, it may mean that you end up with fewer mosquito observations. So quite common, we look at oocysts. Detectable quite early, but often done day 6 to day 8, when survival is not so much of an issue. The question is, however, it's the preferred outcome, but does it accurately predict infectivity? And we've done some work on trying to find out whether there is a bottleneck after oocyst formation. And I think this is may not be particularly exciting work, but it's very relevant. Does a single oocyst render a mosquito infective? If so, a single oocyst is something you want to prevent. And there have been some previous attempts, very valuable work, where oocysts, intact oocysts, and sporozoites were quantified in the same mosquito. But often this was done in lab conditions with very high oocyst densities, and also they looked at intact oocysts. We tried to improve on that by actually visualizing intact and ruptured oocysts, and in the same mosquito examine whether there are sporozoites in the salivary gland. And we diluted our gametocyte culture to reproducibly get into a natural range. Not hundreds, but a few. On average 2-3 oocysts per infected mosquitoes, perhaps sometimes going up to 10, but not higher. And then the question is, these low infected mosquitoes, are they infective? And these are the results of 2 experiments in the bars, where you see on the y-axis the number of oocysts that are not ruptured in white or ruptured in gray. And on the x-axis you see the times after feeding, day 7, day 14, day 21. No rupture before or at day 7, probably day 14, you see that many oocysts rupture, and actually the majority of oocysts rupture, but not all of them do. We found in our experiments with very low oocyst densities that 72% of all oocysts ruptured, and because mosquitoes often had 1, 2, 3 oocysts, that 67 to 97% of all mosquitoes contained at least 1 oocyst that ruptured. So that means that these low infections result in ruptured oocysts. So where do the sporozoites go? We saw a clear positive association between the number of ruptured oocysts and the proportion and the number of sporozoites that made it to the salivary glands. On average, mosquitoes with one oocyst only released 2,100 sporozoites into the hemocoel, and 1,250 on average reached the salivary glands. Keep in mind that a mosquito ingests less than 100 sporozoites on average, so a single oocyst results in an infective mosquito in the vast majority of cases. So now we've agreed on that, one could say we have to move completely to oocyst prevalence. Oocyst density is not relevant. A single oocyst is enough to render a mosquito infective. The good thing is, and some excellent work has been done by Churcher and his group, and he just falls off the, not on purpose, falls off the screen, on better quantifying the association between oocyst density on the x-axis and oocyst prevalence, so the proportion of infected mosquitoes on the y-axis, and there's a very clear positive association. These are findings from the lab in Nijmegen with Stevensai in red and Gamby in green, but you can see it's predictable. So it doesn't mean that oocyst density is non-informative, but it's oocyst prevalence we want to measure. Then the question is, if we can measure it, what's the quality control? And I think that's where we really have to improve. There is a poster where we don't dissect mosquitoes anymore, but we use a parasite expressing GFP and firefly luciferase, and there you can use luminescence to look for oocyst prevalence and density. And then you have a really nice positive control, because you don't need to rely on the mosquitoes, you can actually measure sporozoite quantity, oocyst quantity. In the field, you can have PCR confirmation of single oocysts in natural infections, so to really make sure that what we want to measure, we can also measure with sensitivity. Then the question is, how precise are these estimates? And there are two groups, and there are other good groups, but two of the expert groups, one IRD in Yaoundé, Cameroon, CNRFP in Ouagadougou, that I had access to, where they tried to repeat the assay. So a blood sample from a gamete-site donor, put it in different feeders and see what the variability is. And in Yaoundé, 8 gamete-site carriers were done, 30 mosquitoes examined per feeder, and 6 feeders per person. In Ouagadougou, 50 gamete-site carriers, 50 mosquitoes examined, and 3 feeders. And this is what it looks like. So on the x-axis is just the number of gamete-site donors. On the y-axis is infection prevalence. And you can see there's scatter, and we know there's scatter, but it's actually pretty tight. I mean, one feeder really predicts infection rates in the other. So this is good news. So these are two of the groups that have been doing this for years, and we had a fantastic workshop recently organized by Jajay Jallo and Emily Locke from MVI in Cameroon, hosted by Isabelle Morlet, with researchers from 7 African institutions to generate more expert labs to look at, to really get these accurate and precise estimates of infection rates. So my last slide, I think from the data I presented, we can conclude that oocyst prevalence predicts salivary gland sporozoites. Oocyst prevalence can be determined with acceptable precision, and then it's a question, how do we take this forward? And I think there's a pitfall of having unrealistic caution, saying we cannot really measure this is all too variable. There's variation, you can quantify this, but these are powerful tools. I think the opportunities are realistic caution. We have to invest in oocyst reading quality control, implement confirmation assays like PCR, for instance, and we have to utilize mosquito feeding assays in concert. We have a range of assays. The standard membrane feeding assays, where you normally use oocyst density as a readout, is perfect to select compounds and take the ones forward. But then the ones you want to take forward, you have to test at a range of oocyst densities and really aim to have prevalence as an outcome, because that is what matters in the end. And the advantage, and there have been good examples for PFS 4845, PFS 25, and APM1, these assays also allow you to immediately go to the field. So you have your preclinical study, and you can take your IgG or your plasma and actually test it against natural gamete-site isolates. And I think that's one of the strengths that we should really try to utilize to take transmission blocking vaccines forward. And this is work of a lot of people, also a very active and positive MVI working group. I especially want to mention Will Stone, who's a PhD candidate in my group and who has done a lot of the excellent work that underlies this presentation. Thank you.
Are there any quick questions that anyone would like to ask? Otherwise, we'll hold questions until the end of the speaker presentations.